Hello, this is question 3 from the step 3 paper from 2023. It looks like we got complex numbers here, right? So show that if A and B are complex numbers, B is not 0, S is a positive real number, then the points in the Argand diagram representing the complex numbers that, and that form an isosceles triangle. Right, okay. So A and B are complex, B isn't 0, so A could be 0. Okay, S is positive real number. Right, so we're trying to form a triangle. So really we're just treating these complex numbers as vectors in the complex plane because we're just drawing a shape off of this. So we've got A plus SBI, A minus SBI, and A plus B. So we're going to A. So we go from the origin up to A. Well, with whatever A is, let's call that point A, with vector A getting to it. And then we've got 3 vectors coming off of it, which have to be then forming an isosceles triangle. Okay, right, so let's have we've got these 2 things here. I mean, they've got opposites of each other, which is suggesting symmetry that we're going to want. So if we add that B is, say, x plus yi, and then we do bi, because s is just a scale factor, because that's just multiplying it by a real number. That's just going to increase the length of the vector. So that would give us xi minus y. So we've gone from something which is x, y, that vector, to minus y, or y in the other direction. We've got that and that, and x. So is that perpendicular then, isn't it? I think we're going to be doing, yeah, because you do the gradient of these things. We've got a gradient of the first one is y over x. The gradient of the second one is minus x over y. So we've got something that's perpendicular to B. So we've got, okay, right, that helps. That does help. So we've got BI is perpendicular to B. Right, that is good. So we're going, yes, that just dropped straight out then, isn't it? So we're going to go from O, so A goes from O to A. So let's start off with that. So we've got O, and then we go up to point here A, following that complex number. Then we go to B, because we've got an A plus B. So we then follow B up to point B. Okay, and then we've got 2 equal and opposite vectors plus SBI and minus SBI, which are perpendicular to B. So we'll have that going off one way, that going off the other way. I mean, they could be either way round. Let's say, okay, let's say that's SBI, and then this is minus SBI, and then that is going to give us an isosceles triangle because those 2 sides here are equal to each other. Right, okay, so I haven't actually put together, I mean, I've got a coherent argument there, but I haven't given a coherent answer. So show that those things, yeah, right, forms an isosceles triangle. So we go, so what am I going to say? So I don't know really. I don't know how to put this into words. So if we got A goes from O to A, so let's say point A is vector A from origin. Then we have, then we construct, or then we, I don't know, how am I going to put this? Then we follow 3 different vectors from A. So we go, so 1, 2, 3. So B takes us to B. We could say SBI is perpendicular to B, and minus SBI is perpendicular to B, and then we could say goes to, let's have some more points on this. Well, I don't know, I'll call it S, and this one S prime. And then we can say because SBI and minus SBI are perpendicular to B, SB and S prime B are the same length. Okay, therefore triangle BSS prime is isosceles. Right, okay, as usual with these, or as is often the case, putting it into words is harder than actually working it out. Right, so that's dealt with that first paragraph anyway. Given 3 points which form an isosceles triangle in the Argand diagram, okay, explain with the aid of a diagram how to determine the values of A, B and S so that the vertices of the triangle, essentially that's what I've just done, represent complex numbers that, and that. Right, so if I've got this set up, then so we get this triangle, so we need we want to explain with the aid of a diagram. So okay, so 1, identify the sides of equal length. If I called it, I'll just use the same letters that I had before, S prime. So identify sides of equal length. 2, midpoint of unequal side is A, which is vector A from the origin. Okay, so that's good. 3, B is vector from A to opposite vertex. Okay, and then what else are we in? So it's got A and B, and then S. So SBI. So if that is SBI, so S is the scale factor of B that gives us what, half the base. Okay, right, I've run out of space here. So that's 3. Then okay, I'll squeeze it down here. S is scale factor that multiplies B, well, magnitude of B, I suppose, magnitude of B to give half the base of triangle. So if I call the identify sides of equal length and unequal side equals the base. Right, so let's just see if all that fits together. That seems to have everything. So you identify the sides of equal length. The unequal side is the base. The midpoint of the unequal side, which I could have called the base, is A, which is vector A from the origin. B is the vector from A to the opposite vertex. S is the scale factor that multiplies B, the magnitude of B, to give half the base. Yeah, I mean, that seems fine. Right, that just follows through. So yeah, fiddly sort of opener, but not really much to do with complex numbers particularly. I mean, it's just well, I suppose there is the bit of seeing that SBI is perpendicular to B, but that aside, we're just doing vectors here in order to describe what we need in order to get an isosceles triangle. So, but still, nice start. Onwards to part 2. Show that if the roots of the equation that, where P and Q are complex numbers, are represented in the Argand diagram by the vertices of an isosceles triangle, okay, then there is a non-zero real number S such that that thing holds. Okay, so we've got the roots of that equation are represented in the Argand diagram by vertices of an isosceles triangle. Right, okay, so that means that our roots then are going to be the things that we just had. Why is my pen not working? Oh, I'm on the wrong sheet. A plus B, A plus SBI, and A minus SBI are our roots. So we've got Z minus A minus B times Z minus A minus SBI times Z minus A plus SBI. So that's the roots. So that's equal to 0. And we need, well, if it's got to satisfy this thing, am I just comparing coefficients? Seems likely, doesn't it? P and Q are complex numbers. Right, let's go through comparing coefficients then. I mean, the Z cube obviously comes out fine because we just got Z times Z times Z. So Z squared, I'm going to have so I've got to take, well, one of each of them. One of them is in these, one of the roots each time, because we're going to have Z squared multiplied by the other one. So we're going to have a minus A minus B plus a minus SBI and a minus A plus SBI is equal to 0 because there aren't any Z squareds in this thing up here. So what have we got here? Minus 3A. The SBI's are cancelling, and we got a minus B is 0. Is that everything? 1, 2, 3 A's, a B, and those two cancel. Right, okay, so that's got off to a reasonable start. The trouble is, the ones that are going to be more complicated are, well, this Z to the 1 term is going to be the pain in the neck, isn't it? Because you're going to have loads of permutations or things to multiply together. So we've got to do each pair. So we're going to have 3 pairs multiplied together. So minus A minus SBI, and then minus A plus SBI, and then a minus B. I probably could have left out a lot of these minus signs actually, but still, it is what it is. It doesn't really make that much difference. What have I not done? The plus SBI, and that is equal to P. Okay, so A squared plus S squared B squared plus, oh, that's going to cancel. So A squared on the next pair of brackets, plus B times A plus SABI, and then what am I getting? Then an SB squared I. Okay, then I've got another A squared. Then I've got a BA again. Then I've got a minus SABI and a minus SB squared I. Okay, that's equal to P. So I've got that thing, that thing, that thing, and that thing all go away. So I've got 3 A squares, that one, and that one. So 1, 2, 3 A squares. Then I've got how many BAs? 2 of them, that one and that one, plus 2BA. So that just leaves an S squared B squared. S squared B squared equals P. Okay, so that's good. And then I want to do, well, I might as well do Z0. I'm going to need that one as well, aren't I? So that's just multiplying all of the roots together. So minus A minus B, minus A minus SBI, and minus A plus SBI, and that's equal to Q. So, well, I'll do the second 2 brackets first because I'm going to have a lot of things cancelling out of that. That's just going to be an A squared and an s squared b squared, and that's equal to q. So minus a cubed minus s squared b squared a minus ba squared minus s squared b cubed is q. Okay, so yeah, it all looks fairly ugly. So what am I trying to do? I'm trying to get, I'm trying to show this thing here, p cubed. Well, I can get rid of b's, I suppose, off of this one. If I say that b is equal to minus 3a off of there, sub into these two, this one and this one, that's going to give me what p and q are in terms of s and a, and then I can eliminate one of them. So yeah, that seems reasonable, doesn't it? So let's go off of the back of this one then and say that I've got 3a squared. So b is minus 3a, so that's going to be minus 6a squared. And then I'm going to have plus 9s squared a squared. So I can factorize, well, that's a well, let's get rid of that first of all. And then say I'm going to have a 3a squared, and then I can say 3s squared minus 1. So I'd like to look at that 3s squared minus 1 because it's sat there and they've cubed it all. Yeah. So the a squareds look like they're going to cancel, and then I've got the numerator. So I can do a similar thing on this one then and have, oh dear, right, so, well, that minus a cubed. So the b squared, that's going to be it will still be minus because I'm going to square that one. So that's going to be 9a cubed s squared. This will then become a plus. So it'll be a plus 3a cubed. And then this one will also be a plus 27s squared a cubed is equal to q. So for a cubed, so I've got 2a cubes there. Let's deal with that and that. And then I've got 18 s squared a cubed is q. So I can factorise the 2a cubed, 1 plus 9s squared, which also fits with what I've got on the denominator. Excellent. So that's q. So now if I'm doing p cubed, well, over, let's put it all in one thing. So p cubed over q squared. So that's going to be 27a to the 6, 3s squared minus 1 cubed over some square in this one. So 4a to the 6, excellent, 1 plus 9s squared squared. Cancel the a to the 6's, and that is it, isn't it? Yeah, they just put the 9s squared and the 1 the other way around. Right, that was pretty standard fare, that was. There wasn't anything that exciting in that. Okay, easy to make a mistake, I would imagine, with that amount of algebra, but there was nothing particularly complicated about that bit. On to the final part, final two parts, right, okay. Sketch the graph of that, okay, fine, identifying any stationary points, right, that seems relatively straightforward then. But, well, say relatively straightforward. Let's see how straightforward it actually is. I mean, usually graph sketching isn't that bad. So let's get a few points on the board for this then. So I'll draw the axes in. So when x is equal to 0, y is going to be equal to what, -1. So that's a starter. So it's going through here at -1. And we're going to get y is going to be equal to 0 when x is equal to 1/3. So we're also going through here at 1/3. We've got a vertical asymptote when x is -1/9. Okay. So it's not quite in scale with my thirds there, but I don't want to squish everything up. So that's my vertical asymptote there. Okay, So what else do we want? Identifying any stationary points as well. So, well, I suppose I'm probably going to want to, am I going to want to expand that out? I'm just wondering if I want to find, because what's happening when things are really big? I mean, I can get dy dx by doing quotient rule. So maybe I should do that. I mean, as x gets enormous, it is going to end up here, because we're going to have something enormous cubed divided by something enormous squared. And that's also going to end up down here because we got a cube. So we're doing something like that. So what's the diagonal asymptote? What's it tending towards? I'm probably going to have to expand out in order to do that. But I'll quotient rule it first, I think. So let's just get the shape of the graph, and then I don't know whether they'd necessarily be bothered whether I've got a diagonal asymptote type thing going on here or not. But anyway, let's do quotient rule. So I'm doing a VDU, so 9x plus 1 squared, and then the du is going to be what, 9 3x minus 1 squared, and then minus udv, so 3x minus 1 cubed, and then dv is going to be an 18 9x plus 1, and then over v squared, so I'm putting that 9x plus 1 to the 4. And what do I do with this? I mean, I've got various things I could factorize out of all of this, haven't I? So I've got a 9, I've got a 3x minus 1 squared, I've got a 9x plus 1, and then that's going to be multiplied by, I've got a 9x plus 1, and yeah, that takes care of all of that first bit, doesn't it? And then I've got a minus 2 lots of 3x minus 1 over 9x plus 1 to the 4. So that is 9, I can get rid of that 9x plus 1 top and bottom as well. So 3x minus 1 squared. Then what have I got here? 9x minus 6x, so 3x. And then a 1 plus a 2, so a 3, over 9x plus 1 cubed. Okay, so what does that mean? That means, so if I want stationary points on all of this, I'm going to have turning points. X is a third, so that gives us a 0 in that bracket, and x is minus 1, because that gives us a 0 in that bracket. So that's the stationary points. Okay. But when x is a third, then we know that it's on the x-axis, y is 0. Okay, so that's already come up. So when x is minus 1, we're getting y is minus 4 cubed over minus 9 plus 1 minus 8 squared. So what's that going to be? Minus 1. Okay, so we've got a turning point. Minus 1 minus 1. Okay, and we've got another turning point here. I mean, it looks like the only way, that's got to be a turning point. What's happening either side of this asymptote? Either side of this asymptote, if we're a little bit bigger, well, this thing's always going to be positive at the bottom, and that's always going to be negative at the top. So we're down here and here, either side of that asymptote. So yeah, it's going to have to do something like that over here at minus 1 with a maximum there. And then, well, if it's only got one turning point, that's going to have to be an inflection. So it's going to have to go up here, inflect, and then come up here like that. Right. So, yeah, best that I can draw it on the screen. So I suppose the only question is, do I want to put in what is tending to as we go off to positive and negative infinity? I mean, if I was going to expand all this out, what am I going to get? 27x cubed minus 27x squared. Then it'd be would it be plus that time? Yeah, we'd have 2 minus 1, so we'd have a 3 and a 3, so plus 9x and a minus 1. And then that would be over 81x squared plus 18x plus 1. So if that's what I've got, then it's going to tend to, well, we're going to need an x over 3 when we divide through to deal with the x cubed terms. So if we got an x over 3, then we need to get, that's going to give me 6x squared. So we need to have a minus 33x squared from the 81x squared. So we're going to have to go minus, how do we get to 33 off of 81? How do we get to 33 off of 81? Well, I mean, 3's go into them. If you divide by, 27, multiply by 11. 11 over 27 times 81. Yeah, that would be minus 33. And then with the 6 and the minus 27. Yeah, so that works out. So, and then everything else is just going to be small because it gets swamped by the denominator, which has got infinities in. So we've got an x over 3 minus 11 over 27 is going to be the, yeah, it's going to be, and it's going to go through, oh dearie me. Right, yeah, so this is really hard to put in. But that's what we're getting for this line that's going through here, this dotted line. I'm not sure it was worth putting that in actually. But that dotted line is x over 3 minus 11 over 27. That's what it's tending to along those lines. But I'm not sure that's really that necessary. I'd have to draw that a bit better as well to go around there. So it looks like it's actually tending towards that as we go to minus infinity. Anyway, I might have just sidetracked myself a little bit too much there. But all in all, I've got the vertical asymptote, I've got the 2 turning points, I've got the points of intersection on the axes. So I think I've got more than enough there in that graph sketch. All right, so on to the last part then. So show that if the roots of the equation that are represented in the Argand diagram by vertices of an isosceles triangle, so what we did in part 2, then p cubed over q squared is a real number and it's greater than minus 27 over 4. So this is clearly linking in with what we did in the last bit. So we've got, or the part 2 bit, so we've worked out this thing here. So this is like p cubed over q squared, which we were calling y. Let's put some stuff in blue here. So this is our y, get the right sheet, y, because that's what we call y, isn't it? That's what we've just drawn, but without the 27 over 4 bit. Yes, and they've changed s squared to x. Okay, so we've got y is, yeah, y was all of that bit. Okay, right, so that's right, okay, I don't know what I'm writing there. So 27 over 4, and they've changed s squared to x squared. So we add that p cubed over q squared is 27 over 4, and then 3s squared minus 1 cubed over 9s squared plus 1 squared. So that's what we've got. So if the roots of the equation that are represented in the Argand diagram by vertices of an isosceles triangle, then p cubed over q squared is a real number. Well, that is a real number because s is a real number. Is that all we did here? Right, so show that if those roots are represented in the Argand diagram, yeah, exactly what they're saying here. So what they've said in this here for part 2 is exactly the condition that we've got here in part 4. So these are the same. Okay, so right, then that is a real number. Yeah, and this is, well, this is a real number. And it seems a bit weird that they're asking, am I missing something on this? That they're asking us, there is a non-zero real number s, yeah, such that that thing works. Yeah, I know. We've just done that. No, that's a bit of a strange one. Right, okay, so from part 2, p cubed over q squared is real as s is real. Okay, so we've got that, and then we need to show that p cubed over q squared is greater than minus 27 over 4. Greater than minus 27 over 4. What does that mean? So how we, I mean, the 20, obviously we've got 27 over 4 just sat there. We've drawn, it's got to be something to do with this graph. So we've got that thing. So we've got, I mean, surely I'm going to be able to squeeze this on. I don't want to start a new sheet. I mean, it doesn't feel like I'm going to need it. So we've got that s squared is equal to x. And we've got that this thing is y. So we've got p cubed over q squared equals 27 over 4 y. Okay, so we're saying that y is greater than minus 1. No, yeah, greater than minus 1 is what we want in order to show this result. Y is greater than minus 1, right? So it's anything up from here. I mean, at least that's fitting in with something to do with a graph. So what am I missing here? What am I missing? So that's only for, oh yeah, it's for positive x. Positive x because we've got an s squared. Right, okay, yes, s is real. Right, so from 2, we've got that is real because s is real. Then we can say, therefore, s squared is greater than 0. I'll put is there, as s is real. And then we can say, therefore, x is greater than 0, as x equals s squared. Right. Okay, so that seems good. In which case, we can say, therefore, y is greater than minus 1. Yeah. Which means, therefore, p cubed over q squared is greater than minus 27 over 4. Perfect. Right, okay, that was a little bit fiddly trying to put that together at the end. Yeah, it was just trying to, I think as soon as that bit was in place of seeing exactly how, it doesn't help having this on 2 sheets really, of what they had put previously in part 2 for the p cubed over q squared. But yeah, once you draw parallels between this and this, what we've just sketched out, seeing that that's 27 over 4y, then it does kind of push us into a corner of what y is going to be off of that inequality, which certainly helps to unpick it. But that was a reasonable sort of question, I think. I mean, that last part I think was a bit tricky. The graph sketch was straightforward in part 3, and you probably would get a fair few marks for that, but that was just gimme marks part 3. Just as part 2, you get a lot of marks, but that was gimme marks as well, because there was nothing difficult about it. Part 1, okay, he was trying to put it into words, but providing you're happy with using complex numbers as vectors in that way, you know, it's not a lot to put together. It's just trying to phrase it logically on the page. So part 1 was a little bit sneaky, but 2 and 3, I mean, that's a lot of marks for not doing very much, really. And then part 4 just needed a little bit of detective work. But all in all, that was quite a nice question.